Hello again. So we're going to look at verifying identities this time. This is one of those skills that takes a fair amount of practice, and it's one of those skills that we're practicing so we can get better at our general manipulation of trigonometric expressions. You won't be doing a lot of trigonometric identity verification as you go on in your careers, most of you. But the skills that we learn in working with manipulating these is going to be very valuable as we work on other things. So it's kind of a skill building exercise. So keep that in mind so far as if you struggle a bit with this section, that's totally okay as long as you're getting that practice in manipulating. That's really what we're looking for. So we have a list here to start of the primary identities that we've been working with are quotient identities, reciprocal identities, the Pythagorean identities that we've worked with a fair amount. These even and odd identities we've read about and talked about once or twice, haven't done a lot with, and usually don't come up too terribly much. But this did come up in our arguments about symmetry while we did some graphing. And they're kind of handy. If we have negatives inside, well, can we get that negative outside? Well, on some of them we can pull the negative straight out, like cotangent and tangent. We can just pull that negative straight out because they're even functions. Cosine and secant, notice the negative just disappears because they're even functions. Sorry, tangent and cotangent are odd functions. And sine and cosecant, also odd functions. That negative can just pull out. Very handy. As we work on establishing these identities, you'll notice we will very much focus on manipulating one side of the identity to turn into the other. We're going to try to show that two things are equal. So we can do that by rewriting any portion of our identity using the fundamental identities that we've learned, also any algebraic manipulation skills that we bring to the table. It is generally a good idea, as said here, to begin with the more complicated side. It's easier to simplify complicated things than it is to creatively complicate something simple. So generally, we'll start with the kind of the nastier side and try to simplify it down or clean it up down to the less complicated side if that option exists. One of the reasons, well, there are a lot of reasons why we don't want to be working both sides, and if we go down here, it talks about, when working with one side, we can't add and subtract or multiply and divide things on both sides. There are a couple reasons. One of the big reasons is stated here in your notes. The adding something to both sides of an equation and multiplying both sides of an equation, that is legal because you have equality. Since we don't know equality and we're trying to show equality, assuming that they're equal isn't okay. So saying, hey, these are equal if I add the same thing to both sides, well, we have to establish that they're equal first. So that is one reason. It's a very technical reason. Another fairly technical reason is that often multiplying, even adding, subtracting, but especially multiplying and dividing, often brings in additional domain restrictions that the original problem didn't have. So we're not verifying the identity over its natural domain, we're verifying the identity over a restricted domain based on what we added and subtracted and multiplied and divided. Now, so that's an incomplete verification of the identity. But also, one of the bigger reasons, to be honest with you, is because it defeats part of the purpose of the exercise. Part of this purpose of this exercise is to practice manipulating the expressions, not practice solving techniques. We'll work on solving techniques later. So we want you to just be working one side of the equation, because we want to work on those factoring skills, those algebraic manipulation skills, and the trigonometric skills on one expression to build the other expression. So, that being one of the points of this exercise, we want to make sure we focus on that. So you'll notice that we'll be very restrictive about working one side to show the other. So we're just going to go through some examples here. This skill does take a fair amount of practice, so dive into that practice. We've already done a little bit of it. There was even one early, using identities example on sort of on your test that most of you did really well with. But these are going to get, as you can see, a fair amount more complicated. But how we're going to go about these, we just want to pick one of the sides and manipulate it to look like this other side. So we want to build tangent theta over sine theta into secant theta and show that these two things are equal. As I said, we're going to generally start with the more complicated side, which is why I'm saying we're starting with this side, and we want to show the other. There are generally kind of a handful of nice tools that we're going to use, but in nice small problems, one of the things we can do is we'll just look at what we know. We know that tangent theta is equal to the sine of theta divided by the cosine of theta, and that is in turn being divided by sine theta. So we're trying to simplify this expression. Well, you know how to divide things in fractions if you want. I mean, we could just say those things cancel. They certainly do. But if you're wanting to see it more clearly, and I think that's a good idea, we've got sine over cosine divided by sines. That's going to turn into sine over cosine multiplied by sine's reciprocal, 1 over sine. Could certainly have written cosecant there, but don't want to because I want to show that those sines will cancel, leaving us with 1 over cosine theta. And by our reciprocal identity, that is equal to secant theta, which is what we wanted to show. So that's basically what our process is going to be. Manipulate one side, mess with it, to try to show the other side. Now, a lot of them are going to get a little ickier than this one, but that's okay. That's how we're going to get good at this. So we're just going to run through a couple of examples, and then you'll get your practice at it. I don't know why I'm using purple now. I like colors today. So, to verify this identity, well, again, first thing, we're going to decide what side we're going to mess with, and I certainly think this side is our more complicated tool. And we got to decide how we want to approach this. And two things, to me, stand out. One option is we could multiply this together. We could FOIL this. 1 times 1 is 1. Negative cosine squared times 1 times cosine squared. We could multiply that out together, or all out, and then try to simplify that down. That would probably work, and would be a fine way to progress. However, as soon as we start seeing squared trigonometric functions, it's good to remind ourselves of our Pythagorean identities. You may remember that we have one that says the sine squared of theta plus the cosine squared of theta equals 1. That means, by implication, that the sine squared of theta is equal to 1 minus the cosine squared of theta. So, this 1 minus cosine squared of theta is equal to sine squared of theta, and that simplifies our scenario. Now, is that going to be especially helpful? I don't know yet. One of the things to keep in mind as you're doing these problems is don't try to figure out what will definitely work and build whatever you're trying to build. Just kind of figure out, well, what can I do to manipulate this and do it and see what happens. It's kind of like a puzzle. You're just trying to manipulate it and see what happens. Now from here, again, we could try distributing this sine squared theta, and we'd get sine squared theta plus sine squared theta times cotangent squared theta. And we could do that, but I am trying to get to a single term down here, and that's going to leave me with 2 terms. So it might be nice if we had another Pythagorean identity that would help us manipulate the 1 plus cotangent squared. Anytime we see squared trigonometric functions, particularly with 1s around them, we should be thinking about those Pythagorean identities. So we go look at our list of Pythagorean identities. You've got it on that first sheet, and you'll see we've also got tangent squared theta plus 1 equals secant squared theta. That's just built by dividing each one of these by cosine. And that's got tangent. We kind of really want one with cotangents. So look back at that list again, and there is one that says 1 plus cotangent squared theta equals cosecant squared theta. Again, it's just built by dividing each term here by sine squared. And that looks a lot like what we have. That means we can turn this 1 plus cotangent squared theta into cosecant squared theta, leaving us with sine squared theta times cosecant squared theta. Well, these are reciprocals of each other. Specifically, cosecant squared theta is 1 over sine squared theta. Also, sine squared theta is 1 over cosecant squared theta, so you could have done that as well. But either way, those sine squares are going to cancel, leaving us with just 1. And that's the one we were supposed to show. So again, recognizing that, hey, we have access to some Pythagorean identities there, perform the substitutions based on those identities, and see what happens. I mean, we might not have known that, as soon as we started doing this, we might not have known, oh good, that's going to cancel with a cosecant. But we went about our process, and by the time we got down here and got this cosecant squared, we go, hey, wait, cool, they're going to cancel like we want them to. Great. And again, that's me kind of trying to focus on that. Don't worry too much about finding out what you're supposed to do. Worry about what you can do and play with it and see what works. And you might experiment. Well, what would have happened if we had distributed that? Let's actually do that. See what would happen. If here we instead would have thought, hey, let's distribute that, we'd have gotten sine squared theta plus sine squared theta times cotangent squared theta. Okay. And then I kind of want to simplify this some, but that cotangent, remembering it's cosine squared theta over sine squared theta, is nice. Hey, those sine squared thetas will cancel. Then we'll have sine squared theta plus cosine squared theta, which is our base Pythagorean identity, just written in the other order. Nope, it's actually the same order, sorry. So we know that also equals 1. So that would have worked too. Again, we could have foiled this out too. And you might go through that and see what would have happened. So there's often multiple paths through these problems, and no particular path is correct where the other ones are false, unless you can't get it to work. So don't stress about, like, wait, what's the right thing to do? Just figure out what you can do and try to see what happens. Well, that's got a sine to the third theta. That's going to be ugly. But the reason that these identities work is because this can kind of magically simplify down into this. That's essentially what we're being told, is that this has some nice interaction inside of it that will allow it to simplify down into this. Our job is just to find what that is. So we want to look for it. We're just trying to kind of mess with this and let that little magical simplification thing happen, so we can say, hey, this is really just this smaller thing. So all we have to work with in the future is that smaller thing. So how are we going to go about that? Well, we've got lots of choices. One of the things here, I don't like all this division, so I'm kind of inclined to divide that sine theta into all of these pieces. Now, what's going to happen with that? I don't know. Hopefully, something nice will happen with that. But, I don't know what will happen. We'll see. That will give us cosine theta over sine theta, which will turn into a cotangent eventually. Oh, and we need one, so that might be handy. Plus sine over sine, so sine theta over sine theta, which of course will turn into a 1, minus sine to the third theta over sine theta. Oh, and we'll get some canceling there. So that looks promising. Let's see what happens. Cosine over sine is cotangent, and again, we want a cotangent, so I'm happy about that. Plus sine over sine is 1. I don't have any 1s here, but 1s often work with Pythagorean identities, so that might be handy. Minus, the sine's going to cancel with one of those signs, so sine squared theta. And that structure is going to make me think of our Pythagorean identities. Again, anytime we see a squared trigonometric function, particularly when there are 1s around. And since we have a cosine squared there, Pythagorean identity shouldn't come as too much of a surprise. So cotangent theta plus, and again, we don't often see it as sine, as 1 minus sine squared theta, but if we can look at how we solved it, or back up here. Up here, we're given these forms of the Pythagorean identities, but any manipulation of those forms is valid as well. So cosine squared theta equaling 1 minus sine squared theta is a version of that Pythagorean identity. So is that, subtract cosine squared instead, and sine squared theta equals 1 minus cosine squared theta is a valid version of the Pythagorean identity. Same with these other two. We could subtract the cotangent squared and say 1 is equal to cosecant squared theta minus cotangent squared theta, or any other manipulation of those. So that's why I say whenever we see a squared trigonometric function, okay, maybe it'll be nice and maybe it won't, but we should certainly set a bell off in our heads that says, hey, maybe the Pythagorean identities will come in helpful. So that turns directly into cosine squared theta by our Pythagorean identity, and that's what we were supposed to show. So good. This one's a little bit ickier in some ways, particularly in the idea of figuring out like which side is more complicated. They're basically the same amount of complication, so trying to decide which side to start with has got to be one of our kind of first jobs here. I'd rather, I think, start with this side because I can kind of automatically see some things to try doing. Though starting with this side would be totally okay. So really either one is fine, but I think this one will be a little bit more, I want to say, intuitive, but not necessarily. Let's try. Let's just try to manipulate this and see what happens. So certainly we've got 1 over sine x plus cosine over sine x if we want to split that apart. Again, I want to stress, I don't know if that's going to be helpful or not. It might not be helpful. But it's certainly true. Well, that does turn this into a cosecant x plus a cotangent x, which, again, while true, is not really getting us any closer to what we want. So maybe that's helpful and maybe it's not helpful. It certainly doesn't look like it's going anywhere helpful. But that's okay. We tried something. We tried something that didn't seem to go anywhere. Okay, let's try something else. One of the things we might notice is that this 1 plus cosine x, again over sine x, that 1 plus cosine x looks like it's trying to be one of our Pythagorean identities. Now again, our Pythagorean identities would be 1 minus cosine squared x. And we don't have a 1 minus cosine squared x, we have a 1, great, but it's a plus, not a subtraction. And more importantly, this is not cosine squared, this is just cosine. But this is half of our Pythagorean identity. If you remember your factoring, how to factor a difference of squares, this is 1 plus cosine x times 1 minus cosine x. Because remember, a squared minus b squared is a plus b times a minus b. So we've got 1 squared, if you want to think of it that way, minus cosine squared. It's a difference of squares, and it would factor into these pieces. So we have one of those pieces. If we want to build a Pythagorean identity, we can multiply by the other. And you might remember the vocabulary for conjugate pairs. These are conjugate pairs. They're conjugates of each other. Now, of course, to multiply it on top, we have to multiply it on the bottom. We can't do it to both sides. Again, that's against our rules. But notice that's going to build the 1 minus cosine we want on the other side. So that's kind of handy to recognize. So that makes it feel like this might be a good direction to go. Now if we FOIL this top together, we're going to get 1 minus cosine squared x, because that's what the conjugate pair is FOILed into, over sine x times 1 minus cosine x. Now, as I mentioned before, I like the 1 minus cosine x because we want one of those eventually. But we do have a lot of other stuff here, but our goal in multiplying by that conjugate was to build that Pythagorean identity, so let's take advantage of it. The 1 minus cosine squared will turn into sine squared x over sine x times 1 minus cosine x. And hey, that's nice. Those signs will cancel. And that's going to leave us with the sine of x over 1 minus the cosine x, which is what we wanted. So this approach was a fine idea, I think. It just didn't start going anywhere handy. Seeing the 1 plus cosine on this side and the 1 minus cosine on that side is a big clue that conjugates building Pythagorean identities might help. But even without that, just seeing a conjugate pair or one of the conjugate pieces for a Pythagorean identity is often enough to kind of push us towards that maybe being a handy tool. And that can be a hard one to see. The fact that we're kind of keeping an eye out for those conjugate halves is not an easy thing to get used to doing. But it does often end up being very helpful. Well, this one's certainly nice in being clear what side to start with. Say, for example, if somebody wanted to start with a 1 and open up a 1 into something more complicated, you can do anything with a 1. You can just turn it into tangent to the third x over tangent to the third x and then start messing with that. There's too much creativity in starting with the side that's simpler. If we start with the side that's more complicated, there's more kind of direct action we can perform. So that's good. Let's see. Looking at this, we've got squared trigonometric functions. So that should certainly key off Pythagorean identities might come in handy. Pythagorean identities are, especially right now, kind of our big heavy hitter identities. So they're really the big ones that we should be looking at. So some of those Pythagorean identities might come in handy, particularly if we look back up, cotangent and cosecant are kind of part of those Pythagorean identities, like those one that links those two. So that's kind of nice. But we might see other things first. You might think about the problem we had before and say, hey, this is something squared times something else squared. And you might think, well, hey, we could factor that into cosecant alpha minus cotangent alpha times cosecant alpha plus cotangent alpha. And that's totally true. That can turn into that, no problem. The question is, okay, does that then end up being helpful? Well, maybe it is, maybe it's not. Cosecant is 1 over sine, so 1 over sine alpha, if you want, minus cosine alpha over sine alpha, and then 1 over sine alpha plus cosine alpha over sine alpha. If we wanted to, well, that does give us common denominators in both of those, so I guess it's not the end of the world. 1 minus cosine alpha over sine alpha times 1 plus cosine alpha over sine alpha. Now notice, hey, we've got conjugate pairs again, so if we did multiply that top together, it would be 1 squared minus cosine squared alpha over sine times sine is sine squared alpha, and 1 minus cosine squared alpha is sine squared alpha over sine squared alpha, and that does equal 1. So that would work. That approach would work. It bothers me a little bit that we're taking it apart into factors and then putting those factors back together. Just from an elegance perspective, that bothers me a little bit. But it certainly works. And you'll often get the advice, particularly from people in tutoring centers, to just turn everything into sine over cosine and kind of brute force multiply everything together and make things work. And that can work. But it often makes problems that are quite a bit longer or get quite a bit messier than they have to. But it is kind of a default. If you don't know what else to do and you're not sure what else to do, go ahead, try turning everything into sines and cosines and see what happens. But it is often nice to take advantage of the manipulation that you can get from cotangents, cosecants, secants, and tangents. For example, as we mentioned before, your Pythagorean identities, your primary Pythagorean identities, sine squared alpha plus cosine squared alpha equals 1, and any of its manipulations. Tangent squared theta plus 1 equaling secant squared theta by dividing each of those by cosine squared. Or instead, divide them all by sine squared and get 1 plus cotangent squared theta equaling cosecant squared theta. We lose access to those two manipulations if we're in the habit of just taking away everything and replacing them with sines and cosines. And we can use that manipulation here. Notice we have a cosecant squared here and a cosecant squared there. So if we wanted to, we could just say, hey, that cosecant squared alpha is 1 plus cotangent squared alpha. So 1 plus cotangent squared alpha, and then minus this cotangent squared alpha. Well, and those automatically cancel and turn into a 1. 1 plus 0 is 1, and we're done. Heck, we might even notice that if we subtract, since this is a known equality, it can be manipulated, and that is the reason we can manipulate these identities, both sides, where we can't manipulate the ones we're trying to verify. This is a proven identity, so we get to manipulate it. But this is really just a manipulation of one of our Pythagorean identities. But we can prove it directly very quickly. So notice this worked and was kind of cool, actually. But taking advantage of our secondary Pythagorean identities certainly can make this a much faster problem. So be careful about that common piece of advice, or that common instinct of just change everything into sine and cosine and brute force it. It will often work, but it's often a lot uglier. So try to keep that in mind. Okay. Ooh, what side here is uglier? Well, we certainly know that factors. So it's a difference of squares, so maybe trying to attack that would be a good idea. I mean, we could certainly turn that into 1 minus cosine x, 1 plus cosine x. But whether that would be helpful or not is kind of questionable. We also know by our Pythagorean identity that that's equal to sine squared x. So it might benefit us instead to try to take this side, which does have a lot going on. If we can turn this side into sine squared x and then turn it into 1 minus cosine squared x using our Pythagorean identity, then we'll be in good shape. So trying to turn that into sine squared x is probably a good path. So notice I'm playing with what both sides can become, but I'm still not adding the same thing to both sides, not multiplying the same thing by both sides. I'm looking at what both sides, how they manipulate to come up with a plan, which is fine. Just don't be working both sides of our equation. And if we're going to turn all of this into sine squared, then it might actually be nice to look at everything in terms of sine and cosine. That tangent would be sine of x over cosine of x. And all these things are just multiplied together, so we can cancel those cosines out and get sine x times sine x is sine squared x, which, according to our base Pythagorean identity, is 1 minus cosine squared of x, which is what we were trying to show. So that's not a bad one. How many of these do we have? We got 3, 4 more, 4 more, 5 more. Cool. Where are we? Okay. Well, certainly clear which side to start on this one. Again, we're always trying to start on the more complicated side. So certainly going to start over here and see what happens. I really don't like this kind of +1 down here. I don't like the multiple terms in my denominator. But the fact that that 1 is linked with a tangent squared should make us think again about our Pythagorean identities. So looking back at that and seeing that tan squared, this is beta, but my general rule, use theta, +1 equals secant squared theta. So performing using that identity to perform a substitution is probably going to be helpful. So that's going to be tangent squared beta over secant squared beta. So that's nice. We could have turned this tangent into sine over cosine, this one into sine over cosine if we'd wanted to. But again, I wanted to take advantage of that Pythagorean identity. But since we're looking for something that's purely sine in the end, it probably would be okay for us to look at this as sine squared beta over cosine squared beta. All over secant is 1 over cosine squared beta. Which means we can multiply by the reciprocal of that and get cosine squared beta over 1. So those cosines are going to cancel, and that is going to leave us with a nice sine squared beta, which is what we wanted. So this was kind of a hybrid. Turning everything into sine over cosine just by default at first, we wouldn't have been able to take advantage of that nice Pythagorean identity for the secant squared. But as soon as we did, particularly knowing we were going for just an argument in terms of sine, then turning our tools into sines and cosines to get those cosines to go away, worked out quite nicely. Ooh, that's a little uglier. That's nice. Now we're starting to get a little bit nastier. So, certainly a lot going on this side. You commonly see examples where the left side is the side we're going to work with. But try not to just do that by default. You really do want to look and see which side might be easier to manipulate. But in this case, as with most of our cases, it is the left side. So again, you're just looking for things that might be helpful. You know, this is a fraction being subtracted by a whole number. So a tempting thing to do might be, hey, I'm going to get common denominators here and go 1 minus cosine theta over 1 minus cosine theta. That's 1. It's just with common denominators. Minus sine squared theta over 1 minus cosine theta. I mean, that might be a weird thing to do, and frankly, it is a little bit of a weird thing to do. But it might work. But then I'll have 1 minus cosine theta minus sine squared theta over, over that common denominator. And that starts to look like that might not be as helpful as it could be. But often getting common denominators is helpful, so not necessarily a bad idea. We might notice that 1 minus cosine theta is one of the conjugate pairs for our Pythagorean identity. So multiplying the top and bottom here by the conjugate, by 1 plus cosine theta and 1 plus cosine theta, and seeing what happens there might be helpful. But I kind of, that's going to make that numerator kind of complicated there. So that might be helpful, but not feeling it. But noticing that that's half of our conjugate pair, and that this sine squared is equal to 1 minus cosine squared, which is the entire piece that's one of the conjugates for, that looks much more like it might be a good direction to go into. So I'm going to turn that sine squared theta into 1 minus cosine squared theta over 1 minus cosine theta. And then factor that numerator into 1 plus cosine theta times 1 minus cosine theta over 1 minus cosine theta. And that's really nice. That's going to get those denominators to cancel. I didn't want those denominators anyway. Get 1 minus 1 plus cosine theta. Make sure to distribute that negative. 1 minus 1 minus cosine theta. Those subtract away. And we get negative cosine theta. That's what we wanted. So a couple of different ideas on ways to go with that one, but I think that was probably the nicest one. And I'm trying to emphasize those things so you can kind of see the different kinds of things we should be looking for and kind of what the kinds of questions you should be asking yourself, what kind of things we should be thinking as we go through these. Ooh, that's cool. I know. I'm a geek. I find these things fun. So, this is certainly the side that we're going to mess with. And there's a big danger in this problem. The big danger is, hey, you've got like this sine x plus cosine x squared. The temptation to turn that into sine squared x plus cosine squared x it's going to be a big temptation in doing the same thing here and saying this is sine squared x minus cosine squared x. Just kind of distributing that square. You know you can't do that. But oh, it's going to be tempting at this point. Like, if you have, x plus 5 quantity squared, that's not x squared plus 25. You can't do that. You've got to FOIL that thing out and get, the x plus 5 times x plus 5. So you get x squared plus 5x plus 5x plus 25. So x squared plus 10x plus 25. That square of the first, twice the product, square of the last, kind of thing. So you've got to FOIL them out, but it can trick you really easily seeing it in this form to just want to square the pieces. And that's one of the reasons we're practicing this. We're trying to get our trig skills and our algebra skills to communicate with each other. So it might look a little ugly to start with, but that's what we've got to do with these things to break them apart. We've got to FOIL them out completely. So that's going to be sine squared x minus 2 sine x cosine x's. Again, square of the first, twice the product, square of the last. So plus, because negative times negative, so plus cosine squared x. So that's the first one multiplied out, plus sine squared x plus 2 sine x cosine x plus cosine squared x. So that looks ugly at first. We multiplied all that stuff out. But notice we've got a negative 2 sine x cosine x and a plus 2 cosine x sine x. So those are going to undo each other, leaving us with a sine squared x plus cosine squared x plus this sine squared x plus cosine squared x. And if you remember your Pythagorean identities, each of those is a 1. And 1 plus 1 is 2. So don't be afraid to multiply stuff out and make it a bit uglier for a minute. Sometimes multiplying it out and getting that kind of ugliness is what you need to do to kind of get everything to simplify down the way you want it to. Okay, it's our last one. Now, I do go through these pretty fast. You're not going to be going through them this fast. It does take quite a while and kind of a lot of fighting with and thinking through different strategies. That's why I'm trying to give you kind of insights into what things to look for and kind of questions to ask yourself. But it really does just take some time and some practice. See. I think I still want to start on this side because it does have multiple terms, and it's easier to bring two terms together than it is to break one term into two terms. Two terms being things that are added and subtracted. There are two pieces here, but they're factors. So it's easier to bring two terms together than it is to take factors and break them up into terms. So I'm going to start here. But how do we bring multiple terms together? Well, to be able to perform that addition, I really want common denominators. You might be saying, well, there aren't any denominators, but remember, tangent does have a denominator, and cotangent does have a denominator if we want to build one. Then our common denominators, we'd have to multiply this by cosine theta over cosine theta. And this side by sine theta over sine theta to give us that common denominator of sine times cosine. So that's going to give us a denominator of sine theta cosine theta. But look at our numerator. Sine times sine is sine squared theta, plus cosine times cosine is cosine squared theta. And, oh my gosh, what's sine squared theta plus cosine squared theta? I heard you all shout 1 all at once, which is great. Sine theta times cosine theta. Well, that might not look quite like what we have here, but remember, 1 over sine is cosecant, and 1 over cosine is secant. So this is secant theta from the 1 over cosine times cosecant theta from the 1 over sine, and that's what we were trying to show. Now, I really like this example as an example for us to end on because it's surprisingly common. Recognizing that we have two terms here and only one term on the other side, the way we turn two terms into one term is by forcing an addition to occur. So we force ourselves to have denominators so we can force common denominators. Now we've brought this into one complicated term, hoping something nice happened in that numerator to get it down to one nicer term. And yeah, it is kind of like coincidental that something nice happened there. But remember, that's the goal of these identities. There should be some nice part of the relationship that made it simplify into something nice. We're trying to give the opportunity for that expression to show that nice relationship. So something nice should occur. We just need to give it the chance. Okay, play with these. They do take a fair amount of practice. Try not to get overly frustrated with them if they give you some trouble. That's very, very normal. And do keep in mind that the main goal isn't to necessarily master this process of verifying identities, but just to get yourself used to and comfortable with the types of manipulations that we use. So as we go on, you get more comfortable in manipulating your trigonometric expressions. Okay, keep at it. You might consider reviewing inverse functions from your Math 111. We're going to be doing inverse functions next, and that can be a little bit sticky. So think about reviewing over that, and have a beautiful day.